In many body perturbation theory, electron correlation is treated as a series of correction to an Hartree-Fock reference, and it is based on Rayleigh-Schrodinger perturbation theory, which you have already read in your quantum mechanics class. So, what it does is that it put a small perturbation to the Hamiltonian, and the change to the eigenvalue and eigenfunction are then expressed in series. So, the starting point of a system is to get a 0th order Hamiltonian for which the eigenvalues and eigenfunctions are known, and then you can actually express the correction to the energy and eigenfunction in successive order. And when you use the Fock operator as your 0th order Hamiltonian, that is called Møller Plesset perturbation theory. The Møller Plesset perturbation theory is a special case of Rayleigh-Schrodinger perturbation theory where your H0 is Fock operator. So, what is done is that you put a very small perturbation, and the way it is expressed is that you express the exact Hamiltonian as a 0th order Hamiltonian for which you already know the solution, and a small perturbation V where lambda is an order parameter, and now you can express the Schrodinger equation by replacing the exact Hamiltonian by the perturbed form of the Hamiltonian, and also can replace the wave function by their order by order expansion. Now, this relation is an exact relation. There is no approximation taken up to now, and generally this wave function phi in this case are expressed in the order by order. So, this is 0th order, 1st order, 2nd order, as well as the energy is also expressed 0th order, 1st order, 2nd order, and can go on up to nth order. If you do not truncate the series, this is an exact relation, and the wave function of H0 are generally taken to be normalized. So, what is called an intermediate normalization. So, in this case my phi 0, that is a 0th order solution, is normalized with respect to the full wave function. The full wave function itself is not normalized, so it is called an intermediate normalization, and that is generally used to solve the Møller Plesset perturbation theory. Now, the 0th order Møller Plesset perturbation theory, we have already discussed. The 0th order unperturbed Hamiltonian is Fock operator, and this is how the Fock operator is expressed. It actually has a 1 electron term and then an 1 electron average interaction potential. And this perturbation to the 0th order Hamiltonian is named as a fluctuation potential, and in the Møller Plesset perturbation theory, it is expressed as the difference of the 1 by R12 term minus the 1 electronic average form of this interaction, that is you get in the Hartree-Fock picture. So, now let us go back to the Hartree-Fock picture. In the Hartree-Fock picture, what is done is that the 2 electron interaction is expressed by a mean field operator where each electron is moving in an average field on the other electrons. So, I express this one as nu HF. Now, this is an approximation to the explicit R12 interaction, Rij interaction. So, the difference between this operator and the explicit Rij interaction, in this case, that is my perturbation. Now, if I want to express these equations in orders of perturbation, Hartree-Fock approximation is first order in energy. So, E0 is the summation of the eigenvalues of the Fock operator, and we know the Hartree-Fock energy is not same as the summation of the eigenvalues to avoid the double counting, and this is my first order energy correction like any Rayleigh-Schrodinger perturbation theory, and if I add them together, if I actually do the mathematics, that this is what I will get to, minus half of the antisymmetrized Ij integral, and if I add it to the orbital energies, that is what it leads to my Hartree-Fock energy. So, the first contribution to the electron correlation actually comes at the 2nd order, and this is how the energy expression actually looks like. So, it is a square of the integral, and it has a denominator, and this epsilon a b I j. So, epsilon a b are the unoccupied orbital in the Hartree-Fock picture, and the epsilon I j are the occupied orbitals in the Hartree-Fock picture. So, E a and E b are unoccupied eigenvalues of the Fock operator, and I and j, E I and E j are the eigenvalue corresponding to occupied orbital in the Hartree-Fock picture. Now, because the form actually has a denominator which is a separation between the eigenvalues corresponding to occupied and virtual orbital, so you can already see if this difference is very small, then this term will blow up. So, this will be numerical instabilities in this term. So, that means from looking at the equation, you can already tell that if the energy separation between the occupied and virtual orbital in the Hartree-Fock are not good, in that case the second order correlation energies may not be very reliable. And if you think of the second order correlation energy, the first two terms, the 0th order and the first order, actually what is leads to the wave function, and its second order is the first correction what it comes to the correlation energy. And the second order correlation energy is called MP2 or Møller Plesset Perturbation 2. This is the first order correct, and to calculate the second order energy you need to calculate the first order correction to the wave function. The first order correction to the wave functions are often used to get a good approximation to the wave function, and they are generally used to develop better orbitals and what is called natural orbitals. But this MP2 method is very popular, and if you want to see the MP2 energy, you can think it as the second order correction, because the 0th order correction and the first order correction is actually similar as the Hartree-Fock energy. So, the first order does not give you anything additional over Hartree-Fock. So, you need to at least go to second order, and the second order is the correlation energy. Now, the advantage of MP2 is that MP2 recovers around 90% of the correlation energy, which is good, and MP2 calculations are comparatively faster than CI calculations, scales n to the power 5th power of the basis set in absence of any approximation, and you can take approximation to make it much more faster. So, MP2 calculation is one of the cheapest wave function based electron correlation calculations possible. That is why many people prefer MP2. MP2 treatment is size extensive. We are going to discuss in a while what is size extensivity means, but that is essential for accurate calculation of energies and wave function. And MP2 calculations are generally better near the equilibrium, because we have seen that there is an energy denominator which is a difference between occupied and virtual orbitals in the Hartree-Fock. So, if my occupied and virtual orbitals are not very well separated, that can lead to a problem, and when you move away from the equilibrium, so then more than one configuration becomes important, and the separation between occupied and virtual orbitals are generally very small. Demerits: first thing is that perturbation calculations are not variational. So, I have no way to predict that it will go below the exact energy or it will stay above the exact energy. And if you want to look at this table. So, this is H2O calculated at CCPB TZ basis set, and this is my Hartree-Fock energy, and I am doing the perturbational treatment second order, third order, fourth order, fifth order, and I have the full CI limit number. Somehow I have reached to the full CI limit. So, if you can see that in the Hartree-Fock, of course, there is no correlation. Once I start with an MP2, it recovers around 94% of the correlation energy. Good. MP3, the energy still goes down, it is 96.2. MP4, it goes even closer, 100.2. But the moment I go to MP5, the energy again rises up and it becomes 99.6. So, that means even going at fourth order, my energy does not converge. So, it is fluctuating. So, it is very difficult to predict that at which order this perturbation series is going to converge. If your orbitals are well behaved, generally the second order approximation is good, but if your orbitals are not good, orbitals means Hartree-Fock orbital, then your MP2 energies and the wave functions can be very bad, and that is why it depends upon the reference wave function. Especially for open shell molecules, the resulting energies can also suffer from spin contamination, and it can lead to huge errors. And sometimes the spin contamination error at MP2 can be even worse than the Hartree-Fock. So, an MP2 energy, although it is supposed to improve upon Hartree-Fock, it actually deteriorates the Hartree-Fock results, and of course, it can overestimate the correlation energy, because it can go beyond the exact energy that we have seen in the MP4 example. And MP calculations, any order, whenever you are doing away from the equilibrium geometry or treating a system like bond breaking, trying to do a potential energy surface, on a rule of thumb, they are bad. And maybe in some lecture we are going to generate a potential energy surface of a bond breaking, and we will see how bad the MP2 actually performs. So, MP2 can be only used for molecules which has very well behaved orbitals, very well separation between occupied and virtual, and only at the equilibrium geometry. Now, let us perform some MP2 calculation. Let us do a simple MP2 calculation with the water. generate orca input file. Here I will write, in place of RHF I will write MP2. And we are going to use the basis set CCPB-DZ, that is correlation consistent double zeta. Let me save the input file. I need to go to third week. Let me save as water. So, I open my file here, open in terminal. Now, I saved it as H2O. So, now let me open my output file. I can close the Avogadro for the time being. So, this is my Hatry-Fock. My calculation is done. You can see there is a well separation between occupied and virtual orbital. It's around 18 electron, it's little actually higher than 80 electron volt. So, there is quite well separation. Now, here the MP2 module start. So, the first thing is that it is freezing the 2 electrons as chemical core. Remember, water have oxygen and 2 of the electrons in the oxygen, which is at the 1s2, they are core electrons. So, it is now freezing it, and it will do the calculation with the rest of the operator, and you can see it is doing from 0 to 1. And I will do the calculation, and this is the MP2 correlation energy. Remember, the correlation energy is negative, and so if I add it with the Hatry-Fock energy, 76.025, and the correlation energy of 20, so it is 76.228. So, this is the final single point energy. And at the end it actually prints the timing for each of the modules. So, in this present case the MP2 calculation actually takes less time than the Hatry-Fock. We will see once we go to higher basis set how these timings actually behave. Now, so this is a case where the orbitals are well defined, so it was giving good result. Now, see a case where the orbitals may not be so good, and one of the prominent examples is actually ozone. So, let us try to draw ozone, oxygen, okay. So, I go to NPTEL third week and I save it as O3. Okay, I could have directly saved the work output file by going there. Again, I use same basis set CC PVDZ and in place of RHF I can write MP2. I give the name Ozone. O3.INP O3.INP go to the O3.output file. I see the geometry as well as now see the orbitals. Here my HOMO energy is minus 12 and the LUMO energy is negative. The LUMO energies are supposed to be positive, because that is what the gives Hartree-Fock its stabilization. But here in this case the LUMO energy is negative. So, the distance separation between HOMO and LUMO is only 10 electron volt. So, this can be a problematic case for MP2, where my HOMO-LUMO separation is less and my orbitals are not well behaved, my LUMO is negative. I am not saying that the LUMO can never be negative, but most of the cases if your LUMO is negative, it tells there is some kind of problem in your Hartree-Fock calculation. Now, in case of ozone, the total number of electron is 24 and total you have 6 core orbitals. So, somewhere it has written how many number of orbital, 6 electrons are chemical core. So, they are frozen, your correlation energy is negative. Of course, the magnitude of the correlation energy does not really tells you anything, but you can see that it goes from the Hartree-Fock picture, which was 224.1967 now become 224.87. And again, if you go to the end and see the timings, it's still it's dominated by the SCF calculation. So, although the formal scaling is one thing, there is something called prefactors. So, although the Hartree-Fock has a scaling of n to the power 4 and MP2 without approximation has a scaling of n to the power 5, the Hartree-Fock actually has a much higher prefactor. So, the formal scaling actually start to show up when you go to really big system. For a smaller system, it may happen that a method which has a higher scaling but lower prefactor can be much faster than a method which is a lower scaling but has a much larger prefactor. To see how the MP2 performs and how much is the basis set dependency of MP2 methods as well as the electron correlation methods in general, we are going to use the example of methylene. So, methylene ground state is triplet with a bent structure, and the theoretical simulation of triplet methylene has what made the carrier of Fritz Henry Schaefer III, one of the most prominent quantum chemists in our era. So, initial experiment has suggested that the molecule has a linear geometry, whereas Fritz Schaefer predicted the geometry to be bent, and at that time they have faced a lot of flack because their results were not matching with the experiment. And but they stick to their calculation, and after few years it was proved that the experiment has some problems, and actual correct experiment predicts ground state geometry to be bent and that is one of the first triumph of theoretical simulations over experiments. One of my prominent colleagues always quote Max Planck that the experiment is the only truth, everything else is poetry and imagination, and I always tell him that correctly interpreted experiment is the only truth. To interpret that, the experiment may be done correctly, but the interpretation can be totally wrong. And to do the interpretation of the experiment, theoretical chemistry, computational chemistry can be a wonderful tool. And the advantage of methylene is that it's quite small. So even in your laptop, you can do some large Bayesian calculation, as well as it is very accurate value for the singlet-triplet graph. Triplet is the ground state, and the singlet is 9.12 kilocalorie per mole higher. So let us start with the calculation, because we have still not went into the geometry optimization. So I have already given the geometry, you can just copy paste it and use it, and this will give you a good experience how to create the input file by your hand, not using the GUI. So I will copy it, I will go to the notepad, I will paste it, change the formatting here and there. Remember OR calculation, the first line, start with the quotation, and I want it to be MP2. Let us take def to SVP only as the basis set. So now I can save the input file. There has to be a space between the exclamation marks and the MP2, and let me save it. So I call it CH2 triplet def to SVP. Long names may be difficult to run, like typing while running, but this helps you to understand which input file is what. So try to make sure that your input file name is as verbose as possible. So I will save it, and remember to use the extension all file, not txt, and use the word .inp. Let me make a new folder called mp2 assignment. I should have made it inside V3. Inside the MP2 assignment, let me save it. So it's now saved. Close it here. I go to week 3, MP2 assignment. I open in terminal. CH2 triplet def to SVP. So this is my SCF energy. So the advantage is that I will get both the SCF energy and the MP2 energy from the same calculation. So for the triplet, this is my Hartree-Fock energy, and if I go below, This is my total energy mp2. So, this has been for triplet. Now, let me copy the geometry of singlet and repeat the exercise. Let me go to the notepad. Paste it. First line exclamation mp2 def2 s vp space one line space. I can go to save, make sure that it does not get overwritten. Save it as an input file. ch2 ch2 singlet def2 spp so hope the calculation is done. Yes, it's done now. So let me open the output file. Okay, should have had a look at the molecular orbital. They are quite well separated. This is positive. So let me copy the SCF energy. This is the mp2 energy. So we can calculate the energy gap. Actually, an Excel should have been a better option, but for the time being, let us use a calculator. So triplet is 38.8944 183,427. I think this should be fine. Minus 38.523475166 should be fine. And so this is in atomic unit. So for the going to the kilocalorie per mole, I think the conversion is 627.5. The gap comes to be 30. Whereas if I use the MP2 value, it's 38.98663943 minus 38.954350197 should be fine. And if I multiply it by 627.5, it comes 20. So now you can see that at least going to the MP2 limit, the results improve from what is there in the Hartree fog. Of course, depth to SVP is very small basis. So, one need to see the effect of the basis set to get to the correct trend, and there is something more to it up to what digit you should actually report the numbers. You can think it yourself. When we will solve this problem, we are going to show how many digit we should report and how we should take the numbers.